I'm Rahul, obviously, and today I'm going to talk about how to run a container on Perlmutter. And a disclaimer, more than half my knowledge on this topic has come from my preparing slides for this talk. So I have, at best, a 2-day head start from you guys. And if you have any question, I'll try to answer as much as I can. If not, I promise you I'll consult the experts at NERSC whose introductory slides I have stolen, and I will get back to you. Right. So with that disclaimer, let's go ahead. Just a small introduction about myself and what I work. I am an HPC programming model architect in programming environments and models group. There's a lot of intersection between my title and the group I work for, so I obviously fit in that group. Essentially what it means is I work with HPC programming models like Cocos or OpenMP or OpenACC and stuff like that. I started at NERSC as a postdoc and in 2017, and it was fun because that's when we realized we will have NVIDIA GPUs as our next machine, and most of our senior staff were busy with Cori, which is a CPU, so they let us postdocs play around with GPU frameworks, and that's when I learned about GPUs. So before that, I was in Barcelona Supercomputing Center for my graduate studies in Barcelona, Spain, obviously, and that was fun. I got to work with OMPSS, which is another task-based programming model like OpenMP. OpenMP is not task-based, but it has a similar syntax as OMPSS. And I got to learn some Spanish, so that was fun. Right. Okay, just to know, how many of you actually have heard or have idea about what a container is? Okay, I'm assuming almost everybody. Okay, and how many of you have actually used it in some capacity? Okay, almost everybody. Again, great, because my talk is not like on what a container is or how to build a container. It's more like if you have a container or a Dockerfile, how would you run it on Perlmutter, right? What's a preferred solution? What are the tricks and tips and such things? So that's what will most of my talk be focused on. The second bullet point, NERSC container solutions and how to use them on Perlmutter. And what is like the idea of what future of containers at NERSC would be, like some amount of points and discussions on those lines. So, okay, I guess I can then skip this line because if most of us kind of know what a container is, it's more or less like a lightweight virtual environment for your software based on some OS of your choice. And unlike a virtual machine, it doesn't interact directly with the underlying hardware, but interacts with the host operating system and the kernels that go with it. Right? So, and that's why it's lightweight, which essentially means it needs less amount of compute power to run a container. So who can benefit from containers? And thanks to Jan, we kind of know why we need like a encapsulated software environment to run our stuff on an HPC machine. Like suddenly there are upgrades and silent upgrades like default software versions, things that probably is not known to a lot of users, especially in like a system like Perlmutter, which is like open to a wide range of users from different domains. So we get a lot of tickets like, hey, my app was working last week. What happened this week after the maintenance? And they're like, we changed the underlying software, so you probably have to rebuild it. Or if your app is a heavy app and requires a lot of time to rebuild it, container is for you, right? You can fix your software version, your OS version, and every other version of library that you want to, put it in a container file, and that's it every time. So the upgrades that are external, unless there are certain caveats, obviously, because it is going to run on the same hardware as the native software. So unless a driver changes or something like that happens, you're pretty much safe that it will work. It is, to borrow Evan's line from yesterday, Evan Weinberg, I don't know if he's still here, but he said it's, oh, right, okay. So he was, like we were talking and he said, hey, so the general line about a container is build once, run multiple times. is probably not accurate on HPC systems, especially. So it's mostly like build once on the same hardware and then run multiple times on the same hardware, and as long as the underlying like driver versions and OS versions are kind of consistent, right? That's essentially. So if I have, like Jan was mentioning, a new graduate student comes in, right, and you want to tell him, hey, this is how, or her, this is how you build a software, blah, blah, this version, that version, this particular library, and so on, and you both work on the same machine, you can just hand them your container, and that's it. Things can be more smooth from there on. So, some basic container vocabulary, yes.
That's a good question. Why do you change the? I can understand that the Perlmutter was in the build-up phase, and then I can understand that the software should change. Because when we started out, there were certain software was being frozen in, and it just remained the same. And then we could say for somebody who wants the latest software, they should run in the container.
They can run in a container if the underlying hardware supports it. Like for example, let's say the underlying CUDA version is, CUDA driver is only supports until CUDA 11.8, right? And you want to run a container of 12.1 or something like that, then that's going to not work. I'm not sure about backward compatibility. NVIDIA folks are probably more capable of answering that. Like if I have a 12.1 driver and I want to run a CUDA 11.7, I remember once coming up with this warning that if I do that it kind of wants that, it's going to get deprecated soon, so don't use this base image and things like that. So on, yeah. Right. In case I didn't mention it already, thanks to Jan, you can stop me at any point in the talk and ask me questions. Right? It's more of an interactive talk, hopefully. So some basic terminology, and yeah, that will also make us sound cool when we talk to other people about containers. So Dockerfile is, because almost all of us know what a container is, so I'm not going to spend time on what a Dockerfile is, or also called as container file sometimes, right? It's essentially a list of instructions on what your image should be, right? An image is, once you build the Docker, once you run those instructions in a Dockerfile, what you get is an image. A running instance of an image is called container. So when you're inside an image, you're actually inside a container. So image is what you build, and container is an instance of the image. Container runtime is the software that enables all this, like Docker, which is like the most famous container runtime. But there are others like Singularity, Charlie Cloud, Shifter, and so on. I don't think Shifter allows building images, but we'll talk about it later. So registry is somewhere upstream that you store your images, like Docker Hub, so that you don't have to store the images locally, and you can use that upstream registry to pull it to a different machine if you want to. And then, although we say, the inside of a container is encapsulated software and then you don't really interact with something that is on the actual system, you can mount your file systems on that, right? Otherwise, your data that you're actually working on the machine will probably not be available to you, right? So that is what volume mount or bind mount does. Just a sample container workflow. I think pretty much everybody who has worked with this is kind of familiar with it. You have a Docker file, you build the image on your local machine, you push it to a registry, right? An upstream registry, and then you pull it to whichever machine you want to run on. That's the basic container workflow, right? But, no, okay. I think I deleted one of the slides for some reason. But anyway, so that is not going to work on Perlmutter. We don't support Docker on Perlmutter for many reasons. One of them that I thought was the most valid reason was that Docker actually needs root access, and you can't really give root access to multiple users on an HPC cluster. But again, Evan pointed out that Docker is getting better at HPC in that sense, and the latest versions of Docker don't really need to give root access. And it's also getting better at HPC support. But when we started out, we didn't have those Docker capabilities, so we went with other solutions. So the current solution that we are using right now, Okay. Sorry, I did not edit that slide. It's actually shifter that we do. Oh yeah. So sorry. Yeah. So if you do this, it won't work. Like if you pull Docker image, it will not run, right? Because we don't support Docker. So what you want to right. So, right, the topics of why this wouldn't work is kind of what we just discussed. Also, one point that I missed is like how would that interact with your scheduler, like a Slurm system, right? So those considerations were there. So the current solution that we are having that for a while is called Shifter. Essentially, you build your, similar to the Docker workflow, you build your image somewhere, preferably on your laptop or something, push it to a registry somewhere, and then use Shifter on Perlmutter to pull that image and then run that image using Shifter. So that's been used for a while. So again, just to summarize, Shifter is a lot like Docker, but it does not need root access. That is, I think, one of the biggest reasons that we went with that. And it also allows some HPC optimizations. So if you want to start using Docker, start with learning Docker, the software. Sorry, if you want to start using containers, start by learning Docker. And then there is a good tutorial by staff at NERSC about shifters that will give you like a very high-level view of how to write a Docker file, build an image, and follow those steps on Perlmutter. Right. Okay. So does anybody have any questions at this point? Because from here on, I'll probably show a bit of code snippets and like file snippets of how a Docker file would be and how to run that on Perlmutter. Okay. Okay. So this is an example Docker file. Just again, this I'm not going to go in detail about what how to write a Docker file and things like that, but I'm just showing an example of how this works, right? You actually pick up your base image, which is essentially telling you which OS you want your image to run on and what are the software that we want to run on that, right? So this base image for, like in this instance, I'm using CUDA 12.1.1 based off Ubuntu 22.04. So NVIDIA provides a lot of such base images for a lot of use cases, and it's a smart thing to use their base images because they are really good at writing container files. We can do this by ourselves. Not probably, we can actually do this. We can just take Ubuntu and then build our own CUDA and stuff, but we'll probably end up writing a very unoptimized image, like building a very unoptimized image. NVIDIA people have been doing this for a while and they are very smart, so it's better to use their work, right? And be smart ourselves. So. And then after that, just get some packages. It's an Ubuntu, so do some apt install, git, wget, whatever you want to have, right? And then here I'm building mpage, like the upstream mpage, right? I've just got the mpage tar, untarred it, did the configure, make install, and so on. And then at the end, just removed the source files and the build directory, right? You don't want like the image to be too big, so you want to delete unnecessary files from it, right? And at the end, I just cloned some Hello World program to try this out on our machine. So if you look at it closely, I kind of tend to think of it more like a bash script, like with list of steps that you want to do with the run command stuck in between, right? So if you say in bash script you wouldn't need a run command, and you could probably do this you could probably run this as a bash file without, if you just delete the additional Docker syntax, right? So some basic optimizations. The way container works is that every run command will add a layer to your image, and each layer adds an overhead. So the lesser number of layers that you have, the better it is for the image, right? And it will be more smaller, which means it's easier to push and pull from your registries. But if you see, most of the Docker files that you see are kind of always they don't have like one huge single run command, which they have split their run commands into what makes logical sense to them. And one of the reasons where that helps is the container runtimes, that is the softwares that are doing this, kind of maintain a cache of each layer. So let's say I was able to successfully run the layer of apt installs, and then I mess something up in the mpitch configuration and builds, and I fix that, and again start building. It will not build again from the top, right? It'll pick up the layer that's already in the cache for the OS and the whatever apt install software you have done, and only build the mpitch layer again on top of that. So this kind of helps. If you didn't have these two separate run commands, then it would start again from the top, and everything would have will take that much more time. Yeah, just a disclaimer on Perlmutter. This picking up of cache would only happen if you're doing this again on the same login node. So the caches are stored per login node. So if you jump a login node, then this cache would not be there, and it'll just rerun everything from the top. Right, minimize your run commands as much as possible. So how to choose or write a Dockerfile, right? As I was telling you earlier, there are a lot of pre-built images that you can just use out of the box. PyTorch or NVIDIA's different NVIDIA libraries. There are some experimental images that you can just pull from the NERSC registries. If not an image, it'll at least have a Dockerfile that you don't need to write, and you can just build that Dockerfile into an image. The future, in future, we want to have like a base set of images that users can just build off, like a base image of mpitch or OpenMPI and things like that users can just use, pull it from there, and then start building their softwares on top of that. Right now, we don't really have a reliable way of doing it. We have like snippets of how you can write this in your own Dockerfile, but we don't have like a centralized set of base images. Right. So I said that the solution right now that we're using is Shifter, but that is today's solution. We are actually working actively towards a new solution that is better than Shifter called Podman, which is also an OCI compliant container framework developed by Red Hat, right? OCI compliant is, I think, it's just like a standards committee, and the Podman software is based of those standards, right? It's open source and is being used in multiple places. The good thing about it is like it is a drop-in replacement for Docker. So you can use exactly the Docker options and commands, like build commands and run commands and other things, and just replace the word Docker with Podman, and things would just work fine, right?
Is there any, if I were to teach a student today how to do things like this, would I just say, start using Podman?
Yes.
Is there anything that I lose by using Podman instead of Docker?
Lose? No. On an HPC system, no. You probably end up gaining, at least on NERSC machines, because we are supporting Podman. But lose, no.
And on a local machine?
Maybe the support on a local machine is not that at that maturity. I'm not sure. I've never used it.
Sure.
But Docker, just by the virtue of being around for a longer time, may be more mature.
Okay.
And has a more bigger user base, right? So it's probably more mature. I'm not really sure about local machines. Sorry. So one of the advantages that Podman has over Shifter is, if you remember the workflow, we're actually using Docker to build it and then push the image to a registry, and then pulling on Perlmutter using Shifter. So you're actually building your image on a different machine and not on Perlmutter. You can't build using Shifter. So Podman kind of addresses that issue. You can actually build your images on Perlmutter, on login nodes. So you have multiple cores there. You can just do -J8 or J32 or so on. If you want to be a bad citizen, just do all the codes on a login node. Currently, you can only do this on a login node. You can't do this on a compute node, but that issue is being addressed soon. And so Podman syntax is very similar to Docker. And we actually don't even use native Podman. so NERSC staff are actually maintaining, like, have created a wrapper around Podman called Podman-hpc, which is only available at NERSC. And this is essentially adds features that are more important for us, like the GPU drivers and the MPI libraries and so on and so forth. So that comes with Podman-hpc, which is just a thin layer over Podman. Right? So everything that works with Podman will work with Podman-hpc and plus some additional options. So one huge advantage with Podman-hpc is that, if you remember, I was telling you about every run command creating a new layer in your image. So Podman-hpc will squash all those layers into one single layer when you use the right command and put it at a place that is accessible to you from every login node and compute node. Right? That is a huge optimization that has been done with Podman. Then yes, it has custom hooks for MPICH and GPU libraries that are available on Perlmutter, like natively, that you can use inside an image, and I'll show you how to do that. Another big advantage of Podman is that you can actually modify the image at runtime. What this actually means is you can enter into that image in an interactive manner and then do like a git clone of some repo or edit some file or something. Those changes are not persistent if you exit the image or the container, but you can at least do it. This was not possible with Shifter. So if you want to quickly try something in your container, you could do that with Podman, but not with Shifter. So, okay, am I being too boring? Has everybody, or half of you slept? Or if not, then the next part of the talk is mostly about like commands on how you would use Podman on Perlmutter. So before that, if you want to ask any questions or any doubts. Yeah. If not, okay. Right. The first step is you have your Dockerfile and you want to build it, right? You want to build an image out of that Dockerfile. So it's pretty much similar to what you would do with Docker. You would say Podman-hpc and build. Then dot is kind of, right, I'm in the directory which has the Dockerfile. So dot is like the path where the Dockerfile is. And then -t up, and then an image name and a tag for that image, right? So we were building a hello world Dockerfile, right? So let's name the image hello world and then say the tag is just 01, like some tag. Right, so what would, okay. So this is just a snippet of like a terminal snapshot, like I did Podman-hpc build, blah, blah, exactly the same command that I showed earlier. And if you see it starts from Docker, NVIDIA, whatever, it pulls that NVIDIA's CUDA version on Ubuntu 24 and blah, blah, and all those things. And then if you remember, I said that if you have already built the image once, it will store your cache. And this snapshot was taken after I built the image once already. So it's just saying I'm using the cache which already exists on the login node that you ran on, right? But it should work fine. And then at the end, it will say successfully tagged this image hello world with the tag 01, right? So this is it. This is the last successful message that you'll find. Now, once you do a build, you will only have this image on the login node that you actually built the image on. Like, for example, here, I built it on the login node 23. I'll only have that image on login node 23. If I go into a different login node, like 25 or 27, I'll not be able to access that image. So in order to do that, you have to use a Podman-hpc specific command called migrate, and then just the name of the image and the tag. And then that will take your existing image, squash it into a single layer, so that's the squashed image, and put it at a place that's accessible to every Perlmutter node, or login and compute nodes, right? And then when you do Podman-hpc images, you'll see that there are two versions of the same image. One is, and the same name, the only difference being that the read-write options here, read option here is for the one that we built is false, and the squashed image is true. That means you can enter into that squashed image that you built using the migrate command and do your edits and stuff and everything. So those will be the only two differences. Everything else will be same. Was I clear? Yeah. So how would you run this image, right? That's the next step. So I'm showing this in an interactive node, but the options are pretty much similar on a batch node. So just take your SLOC options and put them, or SRun options and put them in the S batch, and that should work in a similar way. So I'm on an interactive node, and then I'm in the whatever, some directory structure. Like in this case, it really does not matter which directory you are in because you're going to run the image. So image will have its own directory structure, right? So I say srun, the options like I want to run on a single node, 4 tasks per node. We have 4 GPUs, right? Podman-hpc --rm. I think what --rm does is it, like when you run the image, it creates a container, right? And you exit that image, that dangling container is removed instead of being on the machine. Like that's what --rm does. And okay, the work did. I think I missed this saying. So if you look at the actual Docker file that I have here, you see in the final part, I say git clone whatever hello world repo that I have, and then I enter into the hello world repo and then do a make, right? That means the executable that is built is actually inside the hello world directory in the image. But when you run the image, you are actually first placed in whatever the work dir path is set here on the top. So if you directly run your executable, it will not be able to find it because it's it's nested inside another directory structure here, and that is a solution to that is this work dir option where you can tell Podman which directory you want to be placed in once you enter the image, right? And then give the image name and the tag, and then just run the executable, right? That's basically right. So you can see this is what you get. It runs the MPI that we built in the container, CUDA 12.1.1. It says very obviously that it's a container image, copyright of NVIDIA, and runs 4 MPI ranks, right? Anybody notice anything weird here? I'll just point it out. There are a couple of weird things, but the most obvious one, I think, at least, is that it is not running 0 out of 4 or 1 out of 4, 2 out of 4, right? It is. So this is an choice that the Podman developers and I think NERSC staff made a conscious choice that when you're running an MPI image inside Podman or some MPI thing inside Podman, it is not creating one MPI world with 4 MPI ranks in it, but it is creating 4 MPI worlds with 1 MPI rank in it, each. And so that's why it's like, if you print out the MPI world size, it will always be 1, but it will do it 4 times. This is an obvious choice that that was made. Obviously, this is not acceptable for a lot of users because they want to know actually how many MPI ranks are being created, and then they have some work distribution based on to that. So what you can do is you can use something called as MPI module available with Podman that will at runtime replace the MPI in your container with the cray MPage, right? So for all that, it's the same set of commands that we saw in the previous slide, except that now with Podman-hpc, you will also add the --MPI flag. And then, as you can see, first obvious thing is it does not run a CUDA image because it's not a container image anymore, but it runs the MPI, 4 MPI ranks, 0 out of 4, and then you get like the right number of things and the right processor number and everything and all that sort of things. Was that clear? Yeah.
Can you explain this in a bit more detail? So what exactly do you replace?
The MPI runtime. So
the libraries are still in the Docker image.
Yes. So instead of saying, let's say, LMPI to the MPI path in your image, right? It says LMPI to the cray image path.
So you basically mount the cray image part
Yes.
into the image
Yes.
and then link to the executable
Yes.
there.
So all your software versions that you build inside your container still remain those versions, still remain consistent. The only thing that changes is the MPI runtime.
But that can lead to incompatibilities if my software was built with the
Yes.
API in this image.
Yeah, so that's another thing that I also noticed is, so I was building, for example, I was inside my container image, I was building mpitch with CUDA support, right? It's like minus enable CUDA, whatever, configured line. And then whatever came up, and then I tried to swap this, and that didn't work because there was like some sort of ABI incompatibility. This is a known issue, we are working on it, right? Justify is still very experimental, Podman, but this is what the direction we are going in. It has a lot of advantages. One of the biggest advantages for me, at least, is that ability to build directly on Perlmutter rather than using my local machine. I find that very, very useful. And these swapping of modules that happen, maybe it's needed, maybe it's not needed. It depends on the user. But right now, at least, we are not able to provide us. Like if you build your mpitch inside your image, and unless you do everything by hand, like build the libfabric stuff and build the PMI stuff and everything by your hand, you cannot use the MPI that you have built inside your image. So it's better to just use the one that Cray mpitch has, for now at least. That's it. I'm always finishing my sentence with "for now." So, yeah. Was this clear to everybody? Can I go ahead? Right. So Perlmutter is a GPU machine, right? We are not just interested in MPI, but we also want GPUs. And as I told you, containers actually use the same drivers as the host machine. So you say, along with minus MPI, you just add a minus GPU flag, which essentially gives you access to GPU drivers. So if you don't run the GPU drivers, I did not show it earlier, but you'll get a warning that the GPU drivers were not loaded, when the container was run. And then similarly, just like MPI hello, I have written like a small CUDA hello, which just goes through all the GPUs of a node and just says, hello, I am this GPU and blah, blah. Right. I'm only printing out like 2 GPU, like not all 4 GPU informations, but just 2 for lack of space and things. So if you can see, it just says, hi, I'm from this processor. I'm this like GPU number 82, whatever. The other one is GPU number 41, and the other 3 GPUs that it sees is like the other 3. You can see like one of them is 41, which is given to a different MPI task, and it sees the GPU number 3, which is 82, which is from the MPI task, the previous MPI task, right? And so on. But this is again just a single node. We are not really interested in single node. We want a multi-node, right? So I just ran a small again example where I said, run this on 2 nodes, 1 rank each, right? To just control the amount of output that's coming out. So you see everything else remains similar like the previous slide, except that the processors are different. This one is on 3473 and the other one is on 3388. Right? So this works as long as you're using the MPI and GPU modules for now. Any questions? All right. So
I try to understand when this Podman was run below not below, like within S-run, how many instances being created when you have 4 MPI -n, for example, -n2, how many container instances being launched? Just one.
if you are using the MPI module. The MPI module is actually just putting you in the path of the Cray mpitch. So it's not using the MPI that we wrote inside our Dockerfile, but the Cray mpitch.
Think about when you load the image, it has a virtual file system which resides in the memory.
Mm-hmm.
So you're saying when I don't use -MPI, I pay that price 4 times, and I use --MPI, I pay that price once.
Could you repeat your question? Well, you have your image in the file system, is that what you're saying? And you create 4 instances of that image instead of 1? Is that your question?
So when you run the Docker image,
Mm-hmm.
are all the files on the disk or in the memory?
On the disk. Why will unless you mount it, you will not really put the path, right?
Okay, then on the disk, so like if I without MPI and without --MPI, that means, well, my knowledge of srun is it run the process for like n times based on -n. So if you run, that means that the Podman-hpc was run 2 times in this case. Does it mean I paid the disk space twice?
No. Podman-hpc would run once. Oh, okay, without MPI.
Without MPI.
Okay, that's a good question. I don't really know. I'll have to find
I
out.
try to figure out the trade-off. Even with -MPI, so what is being, if you think well, naturally I would think that everything still run twice, just the MPI library was somehow smarter enough to figure out it's within the same MPI world space.
Mm-hmm.
But yeah, but if you think it's only run once, I cannot imagine easily how the executable inside the container was aware it's
So there are 4 containers being created.
Mhm.
So like if you're talking about the space that is needed to create 4 containers, then yes, there will be like 4 times that space without the MPI flag. Is that the question?
And -MPI, you think there's only one.
There's only one.
Then how does it know that I'm launching 4 processes of
With the
hello
srun
world?
with the srun command.
The srun is run on top of, is outside the Podman.
Right. So but srun, so MPI is now not a container MPI, but the bare metal MPI, create mpage with the MPI module. And that will have the information.
But is the CUDA hello process run inside the container?
Yes.
So how this process being launched? If there's only one container, it executes a command CUDA hello world. There's only one process being launched, but actually you have 4. So you have 2 in this case. So I was still could not justify how actually srun, this wrapper was dealing with actually launching and container and launching the executable.
That is a more deeper question. I've seen the mapping, and from the mapping that I've seen, all that they do is when it says MPI, they'll replace that L MPI path, whatever, to create MPI, right? And the GTL libraries for CUDA MPI and stuff like that. That is all that is done in the wrapper, at least for this part, as far as I know. If like the question that you're asking, and if I understand correctly what you're asking, I don't really have an answer, but I'll definitely ask and let you know. That's a good
My guess is even with -MPI, it still runs, in this case, two containers. And the difference is it exposes a host list containing all the nodes, while the first case, it doesn't give host file. Like each container gets an individual host file. That's why the visibility is different.
I don't know enough to answer the question.
That's more.
Just to let you know the chronology of Podman options, because there are a lot of options, right? There are srun options, Podman options, and the stuff that goes inside the container, right? So all the srun options are pretty much similar to what you would need without when you're not running a container. So for example, the number of nodes, the number of tasks per node, GPUs per task, and all those options come before the Podman-hpc command, right? Everything that follows Podman-hpc and before the image tag are all related to Podman-hpc, like the module names and the workdir option and everything is processed by Podman-hpc. And everything that comes after the image name and the tag is processed inside the container. So your executable will run inside the container, and like everything else after the image name and tag will run inside the container. So all your Podman options and srun options should all be in that chronological order. First srun options, then Podman-hpc, then Podman-hpc options, and then the options that you want to run inside your container. Okay, now that we have built like a basic hello world, I tried to build LAMMPS inside this image, and this is just, essentially all this is a set of instructions on which LAMMPS version I'm building. I purposefully built like an older, like from 23rd June 2022 LAMMPS, just to show that, container lets you do, you can tell exactly which version of software or library you want to build, then untar it, run the CMake stuff and everything. So CMake is also not available, right? On Perlmutter, you will have CMake, but to get CMake, you need to, again, either install it through apt-get, or in this case, I just got like the pre-built binary of CMake and then just put it in the path, right? And then build LAMMPS with whatever options you want and stuff like that, make manage, then remove the unnecessary source files to control the size of the image, and then use the env variable to set the paths and the library paths in your container or in your image, right? As soon as you enter your image, you need the path to the LMP executable and the library paths accordingly, right? That is all that this Dockerfile is doing, right? I'm assuming all the slides will be shared with you. If you want to try this on, I've actually put a link here. Like this Dockerfile word is actually a link to the GitHub repo where all this is. And I have purposefully not added the top stuff, like where the base image is coming from and things like that, because that is the same that we ran for Hello World. Right. So what I did was I ran the snap potential with 200,000 atoms on 8 GPUs. That is 2 Perlmutter nodes, right? And one thing that we figured out yesterday was, after, like as I was telling you earlier, put the image and the tag, and then everything else will run inside the container, right? So we said LMP with all its, the LAMMPS options, that is the run with Cocos, the neighbor list option, the GPU options, and the NX, NY, NZ, blah, blah, the input file and everything. That is supposed to come here, like LMP, blah, 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 and all those things. But that kind of choked Podman for some reason. We don't know yet. We found out yesterday. And thanks to Stan, and a very smart solution, he said, why don't you try putting all that in a bash file and then run that bash file, right? So I put that bash file, I put all those commands, like you can see the bash file is like just like the, bang bash file, and then LMP, blah, blah, the LAMMPS option for running snap. And I put it somewhere and I pulled it into the container. And then I just said, instead of running LMP, all that command here, I just said bash run this. And this kind of was a very easy workaround. We don't know the reason why the inputs were choked. It may be something that I did wrong, or it may be a Podman issue. We're not sure yet. We just found this out yesterday. Anyway, this ran, and if you see the performance, this is a very, very small use case, but I ran it multiple nodes with the MPI module, obviously, MPI and the GPU drivers and the MPI module. And you see Baremetal is when you're not running this inside a container, and container is when you're obviously running inside a container. And the loop time, which is the metric that we are generally looking for, right, is pretty much similar, and you can chalk hopefully you can chalk this difference away for like run-to-run differences. But I've run this consistently, and this small amount of difference seemed to be present in all the runs. So I don't know if this is the overhead of running a container. But if it is, then it's a very small overhead, in my opinion, at least. I don't know if that overhead will become bigger if we run on multi-nodes, like really large number of nodes. Right. Yes. 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 So we are using Cray MPitch, which is CUDA aware, right? Like the MPI module will swap with Cray MPitch, which is CUDA aware. So, yeah. Yeah. And that is one of the reasons why the MPitch also didn't work, like the one that we built with CUDA, because it could not find all the CUDA aware, the Cray, the HPE specific libraries that are necessary to run the CUDA aware or all those libfabric things. Anyway, right. Current limitations of using Podman is, if I build the LAMMPS image, let's say, I cannot give it to somebody else. I can give you the Dockerfile and you can rerun it and build your own image. And because we kind of know the exact hardware and the software and everything, there is a very high guarantee that nothing will go wrong, right? You can rebuild it with the series of steps that we give and the Dockerfile, right? Cannot use MPI inside a container right now, right? That's the whole discussion we had. Still experimental, I guess. Already mentioned that. So if there are issues, we are very eager to work on them. So if you're using it and you face some issue, please let us know and we will work with you to get it to work. Right. So this is just one slide where I've tried to summarize the main points on what the future of containers at NERSC would, like where the discussions are heading towards, right? It's mainly, can we provide all the softwares in a container environment, right? LAMMPS will be its own container, WASP will be its own container, CP2K will be its own container. And most of these softwares are already, like CP2, I think we already get like a CP2K container. I don't know about WASP. We can build LAMMPS container very easily. So there might be a scenario where all the softwares inside on Perlmutter would be containerized in some form, right? And provide NERSC base images, as I've already said. Like if you want to build your own container, you will have like some base image, like from OpenMPI or MPitch or upstream, like Cray MPitch, upstream MPitch, and so on. Or I think there's an NVIDIA MPI, so on, right? And there's also a scenario where the moment you log into Perlmutter, you'll probably be put in like an image of your choice. Like, I don't know, you want, I use this example a lot, but I've been told that is probably a wishful thinking and not really the use case of containers. But you might want an image with like Ubuntu running fish instead of bash and bat instead of cat and libgrep as like default and stuff like that, and you'll be put in that image. Right. This is, I guess you get an idea of where the direction of this discussion is going on, right? Any questions? Right. The last slide, I said I'll put this up to, is none of this matters if there is a robot uprising tomorrow, right? So yeah, that was good. Right. Thank you.